Flying cars have been promised for decades. From magazine covers in the 1950s to glossy concept videos in the early internet era, the idea has always sounded just close enough to feel inevitable. Anyone who has ever been stuck on a highway crawling along at 2 miles an hour has probably had the same thought. Why not just lift off and fly over the mess? That fantasy has been reinforced for generations by movies, books, and popular culture. And yet, after more than half a century, most people have never seen a flying car outside of a prototype or a carefully staged demonstration. That long gap between promise and reality raises a more serious question. If flying cars were always such a good idea, why did they fail for so long? And just as importantly, why are they suddenly getting serious attention now, with real companies investing hundreds of millions of dollars instead of just producing concept art? To answer that, it helps to start with a reality check. The core problem was never imagination. Engineers have been able to make vehicles leave the ground for decades. The problem was everything else. Energy density, for example, has always been a brutal constraint. Gasoline contains roughly 12,000 watt-hours of energy per kilogram. Modern lithium-ion batteries, even today, typically deliver around 250 to 300 watt-hours per kilogram at the pack level. That is a gap of nearly 2 orders of magnitude. How do you lift a vehicle vertically when your energy source is both heavy and limited? And how do you do it safely, repeatedly, and at a cost that makes any economic sense? This is where the shift toward electric propulsion begins to matter, but also where its limits quickly appear. Electric motors are far simpler than combustion engines. They have fewer moving parts, respond almost instantly, and can be distributed across a vehicle. Instead of one large engine, a flying vehicle can use 8, 10, or even 12 smaller motors. That improves control and adds redundancy. If one motor fails, others can compensate. But redundancy does not come for free. Vertical takeoff demands enormous bursts of power. Many eVTOL-style designs require several hundred kilowatts just to get airborne. The obvious question then follows: how often can you subject a battery pack to those high power cycles before degradation becomes a major operating cost? Looking at real companies helps ground this discussion in something more concrete. Take Klein Vision and its air car. Instead of vertical takeoff, it uses a fixed-wing design and requires a runway, dramatically reducing energy demands. That immediately solves one problem. It avoids the worst battery limitations of vertical lift, but it introduces others. The air car must comply with both automotive and aviation regulations, two regulatory systems that were never designed to overlap. Structurally, the vehicle needs to remain light enough to fly efficiently, on the order of roughly 1 metric ton while still surviving road impacts and meeting crash standards. Mechanically, the folding wing system adds complexity that must work perfectly every time. Klein Vision has demonstrated multiple successful test flights, which is no small achievement. But can a design like this scale beyond small production runs? And can it do so at a price point that appeals to more than a narrow niche of buyers? XPeng approaches the problem from a different direction. As a major electric vehicle maker, XPeng has explored vertical takeoff concepts aligned with the broader urban air mobility movement. On paper, this looks logical. XPeng already has experience with electric drivetrains, power electronics, and software. But vertical flight changes the economics and physics of transportation. Hovering is inherently inefficient compared to forward flight. As a result, many current eVTOL prototypes target practical ranges of around 20 to 30 miles, sometimes less once real-world conditions are considered. Is that range sufficient to justify the cost of infrastructure, certification, and operation? And what happens when battery packs, often costing tens of thousands of dollars, need replacement after a few thousand high-power cycles? Then there is Aleph Aeronautics, which has attracted attention for promoting a vehicle that looks like a conventional car but can take off vertically by rotating its internal structure. The appeal is obvious: a flying vehicle that fits within existing road infrastructure. But this concept highlights one of the deepest tensions in the entire flying car idea. Cars are designed to maximize traction, durability, and crash safety. Aircraft are designed to minimize weight, reduce drag, and generate lift efficiently. Can one vehicle truly satisfy both sets of goals, or does it inevitably become a compromise? Aleph's publicly discussed flight range and payload numbers remain modest, which does not make the idea meaningless, but does frame it as a very specific solution rather than a universal one. These examples point to an uncomfortable but important reality. Flying cars are not blocked by a single missing breakthrough. They are constrained by many small limitations that stack on top of each other. Battery energy density, thermal management, noise, certification, maintenance, insurance. Consider noise alone. Even electric rotors generate significant sound, especially during the takeoff and landing. Urban noise regulations are far stricter than most people realize. Can flying vehicles operate frequently over dense neighborhoods without provoking public backlash? And if they cannot, where exactly do they fit into the transportation system? Economics adds another layer of complexity. Helicopters already exist and solve many of the same problems flying cars aim to address. But helicopters are expensive to buy, expensive to maintain, and require highly trained pilots. Electric flying vehicles promise lower maintenance and eventually higher levels of automation. But those savings must offset battery replacement costs, charging infrastructure, regulatory compliance, and insurance. This is why most serious companies have quietly moved away from the idea of selling flying cars to everyone. Instead, they talk about fleets, services, and controlled routes. Not mass adoption, but selective deployment. Does that make flying cars less revolutionary or simply more realistic? Regulation ultimately shapes everything. Aviation safety standards are far more demanding than automotive ones. A car can break down safely by pulling over. An aircraft cannot. In aviation, failure is a life-threatening event, not only for passengers, but also for people on the ground. That is why certification takes years, not months. In 2019, European regulators introduced special certification conditions for eVTOL aircraft carrying up to 9 passengers with a maximum takeoff weight of about 7,000 pounds. That move signaled something important. Regulators were beginning to adapt to a new category of aircraft. But adaptation does not mean approval is easy, fast, or guaranteed. So when people ask why flying cars are suddenly being taken seriously, the answer is not that the dream has suddenly become easy. It is that the conversation has become more honest. Electric propulsion, modern software, improved materials, and better manufacturing have removed some barriers, but not all. Companies like Klein Vision, XPeng, and Aleph Aeronautics are not chasing fantasy. They are navigating trade-offs. And those trade-offs explain both the renewed interest and the persistent skepticism. Which leads to the more useful question. Not will flying cars replace cars, but where do they actually make sense? How many flights per day would justify the cost? How much time must be saved to offset higher prices? And how much complexity are cities and regulators willing to accept? Flying cars have not arrived as a mass-market reality, but they have crossed a more subtle threshold, from being dismissed outright to being examined seriously. And in technology, that shift alone is worth paying attention to. If flying cars are this complex, constrained, and expensive to build, a reasonable question naturally follows. Why are companies still pursuing them? And more importantly, how could something so costly ever become a profitable business? The answer lies not in mass adoption, but in pricing, utilization, and the kind of transportation problem flying vehicles are actually meant to solve. To begin with, it helps to look at real prices rather than optimistic forecasts. Basic roadable aircraft such as the Samson Switchable are priced around $170,000. More advanced vehicles capable of transitioning between road and air regularly sell for far more. High-end flying cars and car-aircraft hybrids typically fall between $500,000 and well over $1 million. The two-seat air car, for example, has been estimated to cost anywhere from roughly $500,000 to about $1.1 million, depending on configuration and production scale. A separate analysis conducted in the United Kingdom found that the average purchase price of a flying car was approximately £495,000, or around $630,000 US, before licensing fees and additional costs were even considered. That immediately places flying cars in a completely different financial category from conventional automobiles. A $35,000 sedan or even a $100,000 luxury car is simply not a meaningful comparison. Flying cars are closer, economically speaking, to light aircraft than to road vehicles, and that is not an accident. They are built to aviation standards, not automotive ones. The materials, redundancy, testing, and certification requirements are far more demanding. The question then becomes, are these prices a permanent barrier, or are they a reflection of early-stage technology? Supporters often argue that today's prices reflect early production volumes and that costs could fall significantly with scale. Some projections suggest that prices might eventually decline into the $150,000 to $250,000 range as manufacturing matures. But those projections usually come with an important caveat. That scenario is many years away. In the near term, flying cars remain capital-intensive machines built for early adopters, not for the mass market. And price is only the beginning of the cost story. You cannot simply buy a flying car and start using it. Training and licensing add a substantial upfront expense. Estimates from the UK suggest that pilot licensing and training alone could cost around $35,000. That is equivalent to buying another new car, simply to learn how to operate the first one. Is that unreasonable? Not really. You are not just driving. You are flying an aircraft. But it does change the economics. It raises the barrier to entry and narrows the pool of potential private owners even further. Operating costs add another layer of complexity. Maintenance costs for eVTOLs and flying cars remain uncertain because only a small number of vehicles are currently in regular use. Electric propulsion does reduce some mechanical maintenance compared to combustion engines, but aviation-grade components, battery replacements, specialized inspections, and dual certification requirements all carry significant costs. Early estimates for total operating cost in high-utilization urban air mobility scenarios suggest figures around $2.97 per passenger seat mile. Importantly, that number includes both acquisition and operating costs, not just routine maintenance. When analysts isolate direct operating costs, estimates vary widely. Some feasibility studies for electric aircraft suggest operating costs as low as 25 to 75 cents per mile flown. But those figures typically exclude fixed costs, such as insurance, storage, and certification. Other analyses estimate costs closer to $3.50 per mile once all factors are considered. Early projections for eVTOL air taxi services place per passenger mile costs anywhere from about $2.25 to as high as $11, depending on utilization, energy prices, and maintenance assumptions. These numbers are not trivial. So why would anyone think this makes economic sense? The answer lies in how flying vehicles are expected to be used. Profitability does not depend on selling millions of vehicles. It depends on keeping a smaller number of vehicles flying as often as possible. This is the same logic that governs commercial aviation. An aircraft that flies 1 hour a day is a financial failure. An aircraft that flies 10 hours a day can be profitable even if its purchase price is high. The same principle applies here. Flying cars and eVTOLs are not designed to sit idle in personal garages. They are designed for fleets, routes, and high utilization. This is where the value proposition becomes clearer. Flying vehicles are not competing with economy cars. They're competing with time. A 20 to 30 mile trip that takes 90 minutes on congested roads might take 10 to 15 minutes in the air. For certain passengers, business travelers, medical transport, time-critical logistics, that time savings has real monetary value. The question is not whether everyone will pay for it, but whether enough people will. Energy costs further support this model. Studies of electric aircraft suggest energy costs as low as $8 to $12 for a 100-mile flight, compared to roughly $400 in fuel for a conventional aircraft covering the same distance. That difference is substantial. While these figures do not include all costs, they highlight why electric propulsion is so attractive. If energy remains a small fraction of total operating cost, then improvements in battery technology and charging efficiency directly improve margins. Still, it would be misleading to suggest that flying cars are on the verge of becoming cheap. Even optimistic scenarios suggest that per-passenger mile costs might eventually fall to around $1.50 in mature urban air mobility systems. That is competitive with premium ground transportation, not with everyday commuting. And that distinction matters. Flying cars are not about replacing cars. They are about serving specific high-value routes where speed matters more than cost. So why are companies willing to invest billions collectively into this space? Because the upside, while narrow, is significant. If even a small percentage of urban trips shift to air, the revenue potential is enormous. Analysts estimate the global urban air mobility market could approach $1.5 trillion by 2040. That figure assumes selective adoption, not universal use. It assumes fleets, not garages. And it assumes prices remain high enough to support the infrastructure required to operate safely. This brings us back to price. High prices are not a flaw of flying cars. They are a prerequisite. Certification alone can cost tens or hundreds of millions of dollars. Redundancy requirements add hardware. Insurance costs reflect aviation-level risk. Batteries must be replaced periodically. All of this demands pricing that reflects reality, not consumer expectations shaped by the automotive market. So when critics point to six-figure or seven-figure price tags and declare flying cars a failure, they may be asking the wrong question. The more relevant question is whether a limited number of expensive vehicles, operated intensively, can generate enough revenue to justify their costs. History suggests this is possible. Helicopters already do it, albeit imperfectly. Flying cars and eVTOLs are an attempt to improve on that model, not to democratize flight overnight. In that sense, flying cars are not a consumer product waiting to get cheaper. They are an aviation service waiting to become efficient. And whether they succeed will depend less on how low prices fall and more on how well companies manage utilization, regulation, and public acceptance. That is where the real profit or loss will be decided. Looking ahead, the future of flying cars is best understood not as a sudden breakthrough, but as a gradual progression through clearly defined phases. Over the next 5 to 10 years, the industry is likely to remain focused on proof rather than scale. The immediate priority is not mass deployment, but certification, safety validation, and controlled operations. In this phase, flying vehicles will appear only in limited environments, airport to downtown routes, medical transport corridors, and highly regulated urban zones. This is the expensive stage. Capital will be consumed faster than revenue is generated, and most projects will not survive. That outcome is not a failure of the concept. It is a normal filtering process in aviation. If this first phase succeeds, the next stage, the early 2030s, will be defined by standardization rather than expansion. This is when regulators, operators, and manufacturers begin to agree on common rules: noise thresholds, air corridors, vertiport designs, and operating procedures. Costs will not collapse, but they will stabilize. Flying vehicles will increasingly be treated as infrastructure-backed services rather than experimental machines. Importantly, this is also when the industry will stop talking about ownership almost entirely. The dominant model will be fleet-based, with utilization, not unit sales, determining success or failure. Beyond that, in the longer term, flying cars are likely to scale geographically rather than socially. They will expand into cities where congestion, geography, and economic density justify their existence. Mountainous regions, island clusters, megacities with saturated ground infrastructure, these are the environments where urban air mobility makes sense. What they will not become is a universal consumer product. There will be no flying car in every garage. Airspace, noise, safety, and regulatory complexity make that vision unworkable, regardless of technological progress. Flying cars are not waiting for a single breakthrough or a single visionary to make them real. They are waiting for alignment between technology, economics, regulation, and public acceptance. That alignment takes time, and the companies watching most closely are also the ones moving most carefully. Are flying cars a serious next step in transportation, or another expensive solution searching for a real problem? And if even companies like Tesla are staying out, does that signal caution or simply a missed opportunity? We've heard way too much about cheaper batteries, faster charging, 1,000-mile range breakthroughs that are supposedly going to take electric vehicles to the next level, but most of them end up being nothing more than empty promises that never make it into mass production. Out of all these ideas, solid-state batteries are easily the most promising. At the same time, they've also become the most boring to hear about, simply because they're still nowhere near large-scale production, despite countless companies showing off prototypes with impressive specs and eye-catching energy density numbers. We mean, at this point, whenever solid-state batteries come up, people tend to react with a healthy dose of skepticism. But this time, we might actually have a reason to believe the hype, not because solid-state batteries suddenly sound more convincing, but because a reputable manufacturer, Donut Lab, has officially announced mass production. And that's why tech media all over the world are buzzing right now. These are being called the first solid-state batteries you can actually buy today, instead of having to wait until 2030 like so many previous announcements promised. According to Donut Lab, these batteries could significantly improve range, lifespan, and charging speed for everything from electric cars and motorcycles to heavy trucks and construction equipment. So why is this the most credible, solid-state battery we've seen so far? And what exactly makes it special? Okay, we'll get to Donut Lab in more detail later, because this battery really needs to be explained first. Unlike traditional lithium-ion batteries that rely on a liquid electrolyte, Donut Lab's technology completely eliminates it. And yeah, the name kind of says it all. Solid-state batteries use a solid electrolyte instead. According to Donut Lab, this new battery reaches an energy density of 400 watt-hours per kilogram, which is a huge jump compared to the 250 to 300 watt-hours per kilogram you see in today's top-tier lithium-ion batteries.
With Donut battery, we set a new baseline, 400 watt-hours per kilogram.
So far, Tesla's most advanced 4680 battery is only used in the Cybertruck, and even that tops out at just under 300 watt-hours per kilogram. We are not 100% sure, but the latest number we remember is around 272 watt-hours per kilogram. Meanwhile, BYD's well-known LFP blade battery maxes out at about 175 watt-hours per kilogram. That means solid-state batteries are getting close to double the energy density. And yeah, they'd be significantly lighter than both of those options. By now, you probably see why this matters. Most EVs on the road today use LFP batteries. Around 60% of electric vehicles globally run on LFP. The rest use NCA or NMC, which are typically found in higher-end models. LFP is popular because it's cheap and very stable, but its energy density almost never goes past 200 watt-hours per kilogram. So let's say your car currently uses an LFP pack, and you replace it with Donut Lab's solid-state battery. What happens? A 200-mile range suddenly becomes 400 miles, or even more. Realistically speaking, Tesla's best-selling vehicle, the Model Y, currently offers up to 357 miles of range with what's believed to be a 75 kilowatt-hour NMC battery pack. Now imagine buying a Model Y with a range north of 700 miles. Okay, that might sound a little far-fetched, but if Tesla were to partner with Donut Lab, we honestly think it could happen sooner than you'd expect. Elon Musk has never been shy about spending money on better batteries, as long as they deliver on energy density and cost. And sure, we're not even talking about pricing yet, but purely from an energy density standpoint, this is already incredibly compelling. That's the real advantage of high energy density batteries. Put simply, higher energy density means a lighter battery pack and a car that can go much farther on a single charge. So why is this the first solid-state battery to actually reach mass production? Let's hear directly from Donut Lab's CEO.
So the obvious question is, are we shipping this in 2029 or 2030? No. These batteries are available today. Not just available for OEMs to look at in the lab, and not just available to prototype with, but available for real production.
Like we mentioned earlier, solid-state batteries are the holy grail everyone wants, but getting there is anything but easy. The technical challenges are incredibly complex, and the costs involved have forced many manufacturers to walk away because scaling up just isn't viable. We'll break that down in more detail in a moment. According to Donut Lab, their solid-state batteries are already available at gigawatt-hour scale production capacity for companies around the world, something almost no one else has been able to pull off.
In fact, today we are making history because Donut Battery is the world's first solid-state battery in production vehicles shipping to customers.
And it's not just about the 400 watt-hours per kilogram energy density. Donut Lab also claims their solid-state battery cells can be fully charged in around 5 minutes, delivering an experience that's comparable to filling up a gas tank.
This pack charges from 0 to full in as low as 5 minutes. As low as 5 minutes, and still built for longevity.
This number isn't just a technical milestone. It directly addresses the so-called range anxiety that's been holding the EV industry back for over a decade. At this charging speed, drivers would only need a short break before the car is ready for another long journey of hundreds of kilometers. The secret behind Donut Labs' ultra-fast charging lies in its sulfide-based solid electrolyte structure. Unlike traditional lithium-ion batteries, which risk overheating when pushed with extremely high charging currents, Donut Labs' solid material has exceptional thermal stability. It allows lithium ions to move at almost mind-blowing speeds without melting the separator or triggering harmful side chemical reactions. This effectively breaks the physical limits of today's liquid electrolyte batteries, which are typically capped at 20 to 40 minutes of charging in order to protect cell lifespan. Now, charging a battery in just 5 minutes requires an enormous amount of power, likely at least 1 megawatt. That's our estimate, since Donut Lab hasn't disclosed exact numbers. Still, the company claims that despite these extreme charging speeds, the battery is designed to maintain long-term durability and cell longevity.
Donut battery is designed differently. It's designed for 100,000 cycles. Now, that's not just better cycle life. That's an entirely different category.
Yeah, and beyond the fact that it can fully charge in just 5 minutes, the battery's lifespan is just as shocking. Donut Lab claims it can handle up to 100,000 charge cycles without needing to cap charging at 80% like older battery technologies do to protect long-term health. To put that into perspective, Donut Lab compares its solid-state battery to both standard and high-end lithium batteries. Typical lithium-ion batteries in use today, like LFP packs, usually last around 1,000 to 1,500 cycles before significant degradation kicks in. That translates to roughly 3 to 5 years of heavy, daily use. Even higher-end lithium batteries such as NMC, NCA, or Tesla's 4680 cells, which are used in premium electric vehicles, generally top out at around 5,000 cycles. Now, with 100,000 charge cycles, this battery could theoretically last longer than the chassis of a car or even the engine of a motorcycle. If you charged it once a day, it would take more than 270 years to use up all those cycles. We genuinely hope we're not misunderstanding something here. If this doesn't sound right to you, let us know in the comments. So yeah, pushing durability limits by 20 to 100 times isn't a minor improvement. It's a full-on materials science breakthrough. A battery that can survive 100,000 charge and discharge cycles would be a game-changer for consumers and for the entire EV ecosystem. In theory, you could drive up to 10 million miles on a single EV battery. Normally, battery degradation after 5 to 10 years is one of the biggest concerns with electric vehicles, since range slowly but steadily drops over time. And battery replacements aren't cheap either. Today, replacing an EV battery can cost anywhere from $5,000 to $16,000, depending on the battery size, the manufacturer, and the vehicle model. Yeah, it's expensive, and that's a big reason why a lot of people still hesitate to buy an EV. So how exactly did Donut Lab manage to achieve such a massive leap in battery lifespan? We'll try to explain this in the simplest way possible. In traditional liquid-based batteries, every single charge and discharge cycle triggers unwanted side chemical reactions. The liquid electrolyte reacts with the electrodes, forming buildup layers and slowly consuming usable lithium over time. That's exactly why so many companies have been racing to develop solid-state batteries. Donut Lab's solid-state battery likely uses an extremely stable solid ion conducting material. This completely eliminates those side reactions, allowing lithium ions to move back and forth hundreds of thousands of times without changing the battery's internal structure. That level of stability means no swelling, no leaking, and capacity that stays almost intact for decades. But Donut Lab doesn't stop there. They're aiming for something almost unreal, a truly all-around battery. High energy density, ultra-fast charging, long lifespan, and on top of that, they claim the battery won't catch fire even if it's damaged. As we all know, one of the biggest challenges for EV batteries is performance across different temperatures. In liquid electrolyte lithium batteries, cold weather increases the electrolyte's viscosity, making lithium ions move like they're stuck in mud. That's why range can drop by 20 to 40% in winter, and charging takes much longer. But instead of taking our word for it, let's hear what Donut Lab's CEO has to say.
And at minus 30 degrees Celsius, Donut battery retains over 99% of its capacity. And if you push in the opposite direction, heating the cells beyond 100 degrees Celsius, that's 200 Fahrenheit, the result stays the same, over 99% capacity retention.
Oh my God, Donut Labs' solid-state battery is designed to retain over 99% of its capacity, even in extreme conditions, from deep cold at minus 30 degrees Celsius to scorching heat of up to 200 degrees Fahrenheit. And honestly, that temperature range alone would either freeze solid or set fire to just about any conventional lithium-ion battery pack. We've seen and read plenty about solid-state batteries from companies other than Donut Lab, and one thing we know is that solid electrolytes are non-flammable and act as a strong physical barrier against thermal runaway. Still, 200 degrees Fahrenheit is insanely hot, you know. Yet according to the company's CEO, this battery is safe enough that there's no risk of fire, even in the event of physical damage. On top of that, the batteries can be manufactured almost anywhere in the world because they don't rely on rare or exotic materials. So the big question is this solid-state battery actually affordable? Donut Lab hasn't disclosed exactly which materials are used to build its solid-state cells, but the company says the battery is fully environmentally friendly and made from materials that are widely available. Most high-performance lithium-ion batteries today still rely on cobalt and nickel. Cobalt mining is often linked to serious human rights concerns in the Congo, while the global nickel supply chain is largely controlled by just a handful of countries. So the fact that Donut Labs' solid-state battery reportedly does not use nickel or cobalt means it's far less exposed to geopolitical risk. Donut Lab also claims its solid-state cells are cheaper to produce than comparable lithium-ion batteries. While exact numbers haven't been shared, this is an encouraging sign that the technology could show up in mid-range vehicles, not just high-end models, in the near future. Okay, all of this sounds great, but we get it. By this point, most of you are probably still skeptical. That said, Donut Lab is a highly credible company, and it appears their solid-state batteries are already moving beyond the lab and into real-world use. Based on what we know so far, the upgraded Verge TS Pro electric motorcycle is expected to become the world's first commercial vehicle powered entirely by Donut Lab's solid-state battery. The first customer deliveries are scheduled for the first quarter of this year. On the Verge TS Pro, switching to solid-state batteries delivers a very noticeable upgrade. With the same physical battery space, the new high-capacity option boosts the riding range from about 217 miles to 370 miles. Real-world charging time on the bike is also cut to under 10 minutes. According to Donut Lab's CEO, while solid-state batteries are often viewed as a far-off future technology, their solution is already ready for OEMs to integrate directly into existing production lines today. Now, going back to why most manufacturers still can't produce solid-state batteries at scale, there are actually several reasons. The biggest challenge lies at the interface level. Unlike liquid electrolytes, which easily wet and fully cover electrode surfaces, solid materials struggle to maintain perfect atomic level contact. This leads to higher internal resistance and makes the battery more prone to cracking as it expands and contracts during charging and discharging. On top of that, lithium dendrites can still penetrate solid electrolytes and cause short circuits, which requires extremely advanced material solutions to prevent. From an economic standpoint, solid-state battery manufacturing is incredibly demanding. It requires ultra-dry room environments and extremely high assembly pressures, meaning existing lithium-ion production lines simply can't be reused. Above all, we hope this gave you a much deeper understanding of solid-state batteries. The wait may finally be over, because solid-state technology is poised to solve nearly all of the core weaknesses of today's electric vehicles, starting as early as this year. First is energy density. At 400 watt-hours per kilogram, and potentially pushing toward 500 watt-hours per kilogram in future generations, EVs could realistically double their driving range without increasing battery size or weight. This directly eliminates range anxiety, the biggest psychological barrier holding many people back from switching to electric. Once an EV can travel 500 or 600 miles on a single charge, even while towing a trailer and still remaining efficient, internal combustion engines lose almost all of their real-world advantages. Second is charging speed and durability. The ability to recharge in just minutes and withstand tens of thousands, or even hundreds of thousands of charge cycles is truly revolutionary. The battery is no longer a consumable component that needs replacing after a few years. Instead, it can last the entire lifetime of the vehicle, and potentially far beyond. This dramatically lowers long-term ownership costs, increases the resale value of used EVs, and completely changes how consumers think about the durability of electric vehicles. At the same time, stable performance in extreme cold and extreme heat makes EVs viable in virtually any climate, from frozen regions to scorching deserts. With this kind of lifespan, a solid-state battery could stay with a vehicle for 100 years without significant capacity loss. Even when regularly charged to 100%, performance remains stable, something current battery technologies simply can't match. And this is a huge deal. Today's EV owners are often told to limit charging to 80% to preserve battery health, which adds inconvenience and anxiety. Once that limitation disappears, the EV experience becomes simpler, more intuitive, and much closer to what drivers are used to with ICE cars. A longer battery lifespan also brings clear economic benefits. Battery replacement costs, one of the biggest concerns for consumers, are nearly eliminated. As a result, used EVs retain their value much better, helping accelerate the growth of the second-hand electric vehicle market. From an environmental standpoint, longer-lasting batteries mean fewer new batteries need to be produced, which reduces resource extraction and industrial waste. That said, the exceptional lifespan of solid-state batteries also introduces new challenges. Recycling systems will need to adapt to new materials and battery structures. Manufacturers will also have to prove this level of durability under real-world, long-term use, not just in laboratory conditions. Still, if these lifespan claims hold up, solid-state batteries could become a key factor in making electric vehicles more sustainable and more economical than internal combustion cars over the long run. So, are solid-state batteries the end of the internal combustion engine? We think they'll certainly accelerate that transition, and by 2035, internal combustion engines could be largely obsolete. As Tesla fans, we're genuinely excited about the future of battery technology, especially solid-state batteries. Tesla has long been seen as a symbol of innovation in the EV industry, not just in design or software, but in its bold approach to batteries and the broader energy ecosystem. That's why we're hopeful that Elon Musk and the Tesla team will seriously consider researching and investing in solid-state battery technology in the years ahead. What solid-state batteries promise, higher energy density, extremely long lifespan, ultra-fast charging, and stability in extreme temperatures, fits perfectly with Tesla's long-term vision. Building electric vehicles that outperform internal combustion cars in every way that matters. So what do you think about Donut Labs' solid-state battery? Drop a comment below. We honestly didn't really want to cover Tesla's Cybercab robotaxi this much, because at the end of the day it's still not operating at scale and is currently in the testing phase ahead of mass production, which is expected to begin in April this year. However, Elon Musk has been making a series of eye-catching statements about the vehicle, especially after NVIDIA announced Alpamayo, an AI-powered technology designed to speed up the development of autonomous driving solutions, and a direct competitor to Tesla's FSD. On top of that, the Cybercab has now been spotted on highways for the first time. Meanwhile, a more intense issue involving the Cybercab has just surfaced. Tesla has run into trouble trying to trademark the name Cybercab. In a worst-case scenario, the new vehicle may no longer be called robotaxi or Cybercab at all, and Elon Musk could be forced to come up with a completely new name. That's exactly why we're talking about Cybercab today, so let's dive into the details right now. Before we get started, if you don't like this vehicle, drop a 1 in the comments below, and if you are interested, leave a 2. Alright, 2026 is shaping up to be a make-or-break year for Tesla, as its robotaxi ambitions enter a critical phase. As Elon Musk said late last year, the Tesla robotaxi Cybercab will be the company's second biggest product this year, and Tesla is putting a huge amount of focus on it. The increasing number of Cybercab test vehicles showing up in Austin and San Francisco is clear proof that Tesla is ramping things up. The real breakthrough isn't the number of cars, it's the move toward completely removing human supervision. Tesla is aiming for mass production in April 2026, using an ultra-high-speed production line, with vehicles that have no steering wheel and no pedals. Practical steps, like in-car cleanliness penalty policies, also show that Tesla is already thinking through even the smallest details of real-world commercial operations. Even though Tesla's fleet is still relatively small compared to Waymo, Its core advantage lies in building its own vehicles and optimizing hardware costs. Elon Musk believes that keeping human safety supervisors is the biggest barrier to scaling. Once that barrier is removed, Tesla could roll out thousands of vehicles in a very short amount of time. Recently, Elon Musk even claimed that competitors would need many years to catch up to Tesla's self-driving technology. The Tesla CEO said it would take at least another 5 years before the company starts to feel real pressure from rivals. On X, Elon Musk wrote, "The legacy car companies won't design the cameras and AI computers into their cars at scale until several years after that. So, this is maybe a competitive pressure on Tesla in 5 or 6 years, but probably longer." This statement came shortly after NVIDIA announced Alpamayo, a technology that uses artificial intelligence to speed up the development of autonomous driving solutions. Since Alpamayo is also heavily focused on AI, many people have started to speculate that it could become a direct competitor to Tesla's FSD. However, NVIDIA CEO Jensen Huang has spoken positively about FSD and has also clearly pointed out the differences between FSD and Alpamayo. He stated, "Tesla's FSD stack is completely world-class. They've been working on it for quite some time. It's world-class not only in the number of miles it's accumulated, but in the way it's designed, the way they do training, data collection, curation, synthetic data generation, and all of their simulation technologies. Of course, the latest generation is end-to-end full self-driving, meaning it's one large model trained end-to-end. And so, Elon's AD system is in every way 100% state-of-the-art. I'm really quite impressed by the technology. I have it, and I drive it in our house, and it works incredibly well." Alongside the praise and recognition for Tesla, Jensen Huang also pointed out that NVIDIA's Alpamayo is built on a completely different philosophy compared to Tesla. Instead of developing its own self-driving vehicles, NVIDIA provides a full autonomous driving technology stack for other companies to use. He said, "NVIDIA doesn't build self-driving cars. We build the full stack so others can," Huang said, explaining that NVIDIA provides separate systems for training, simulation, and in-vehicle computing, all supported by shared software. The NVIDIA CEO also added that customers can use the platform as much or as little as they need. He emphasized that NVIDIA plans to work with a wide range of companies across the industry, including Tesla on training systems and companies like Waymo, XPeng, and Nuro on in-vehicle computing. So basically, NVIDIA isn't trying to compete directly with Tesla. Instead, NVIDIA announced that Mercedes-Benz, one of Tesla's competitors, will be the first automaker to adopt its self-driving system. Mercedes plans to launch the system on its CLA sedan in the US in the first quarter of 2026. The timing is interesting, since Tesla is also expected to roll out its robotaxi service at scale this year. Mercedes says the new CLA will be capable of point-to-point autonomous driving, but will still require human supervision, which makes it similar to Tesla vehicles equipped with full self-driving. More recently, Tesla's Cybercab robotaxi was spotted testing on a highway in Austin, Texas for the first time. Unlike low-speed testing in dense urban areas, highway driving pushes the AI much harder. It has to process data at high speeds, merge lanes accurately, and make split-second decisions. Yeah, this honestly looks like something straight out of a video game. Cybercab confidently operating on major highways shows that Tesla is delivering on its promise of a fully autonomous system that requires no human intervention. According to Tesla fans who were on site, the vehicle drove smoothly, maintained safe following distances, and executed lane changes decisively. This is especially significant given Cybercab's ultra-minimalist design. No steering wheel, no pedals, meaning all trust is placed squarely in the AI brain. Ironically, while the technology inside Cybercab appears to be working almost flawlessly, its name has run into a legal issue that's both serious and, frankly, a bit amusing. Tesla, a company known for bold moves and long-term vision, has stumbled over something surprisingly basic. It didn't manage to secure the trademark for its own revolutionary product in time. Cybercab was officially unveiled at Tesla's We Robot event in October 2024, marking a major milestone in the company's ambition to build a fully autonomous taxi ecosystem. This wasn't just the launch of a new vehicle, it was a statement about the future of transportation, where humans become true passengers rather than drivers. What's hard to believe is that even at the height of that high-profile announcement, Tesla still hadn't completed the trademark registration for the name Cybercab. In the business world, Especially for large corporations, this is almost unthinkable. Announcing a product, pouring billions of dollars into R&D, manufacturing and marketing, yet forgetting to legally protect the name is like building a skyscraper and leaving the front door unlocked. And that gap opened the door to a truly awkward and almost comical scenario. A beverage company beat Tesla to the punch. Yeah, just 18 days after Cybercab was unveiled, a company called UniV, a French beverage maker best known for alcoholic hard seltzers, quickly filed a trademark application for the name Cybercab in the US, under the transportation category. At first glance, it's hard not to laugh. A company that sells alcoholic drinks is suddenly holding the spot for the name of a cutting-edge autonomous vehicle. But from a legal standpoint, this is no joke. U.S. trademark law largely follows a first-to-file principle, regardless of a company's size or reputation. When Tesla eventually filed its own application in November 2024, the U.S. Patent and Trademark Office, USPTO, was required to consider the earlier filings. As a result, Tesla received a provisional refusal for two reasons: the likelihood of confusion with an existing mark and the presence of a prior application with an earlier filing date. On the surface, the story feels almost like a legal sitcom. But for Tesla, the stakes are very real. Cybercab isn't just a name, it's a brand tied directly to Tesla's long-term strategy, its technological identity, and investor confidence. Losing the ability to exclusively use or protect that name could trigger a domino effect. Increased risk of brand copycats, challenges in global marketing, and potentially long, expensive legal battles down the road. What surprised many people even more is that this isn't the first time UniV has crossed paths with Tesla. The company previously held a trademark related to Tesla tequila, which caused similar headaches for Tesla when it launched its own beverage. To a lot of observers, this looks less like coincidence and more like a deliberate trademark holding strategy. Given the situation, we see Tesla as having two realistic options: either negotiate and pay UniV to withdraw the application, or take the case to court and argue that a beverage company with no real intent to build vehicles shouldn't be allowed to own the Cybercab trademark. That said, knowing Elon Musk's usual playbook, Tesla is far more likely to choose the second route. You know, Tesla isn't exactly known for compromising easily, especially when it comes to matters of principle. A lawsuit could drag on, but it would also allow Tesla to defend its interests and potentially set a legal precedent. Still, most observers agree that this entire mess could have been avoided if Tesla had handled things more professionally from the start. We're also genuinely puzzled by how Tesla let this slip. It's ironic that a company leading the world in AI, batteries, software, and automation would stumble over such a 101-level management mistake. While many small startups with far fewer resources make sure to lock down trademarks before announcing a product, Tesla, a company with over 100,000 employees, somehow let this one fall through the cracks. In the end, this is a reminder that even the biggest and most innovative companies aren't immune to basic errors. Technological breakthroughs can't replace discipline in corporate governance and legal strategy. In an era where brands are incredibly valuable, intangible assets, a name can matter just as much as the product behind it. So for now, Cybercab remains an uncertain name, and if negotiations fail, Elon Musk may be forced to come up with something else entirely. Drop your suggestions for a new name in the comments below. Switching to a few other updates, Tesla Diner has become the latest target of pessimistic rumors. From the very beginning, the diner sparked debate, not because of the food quality, but because expectations were sky-high for a concept that had no real precedent. Some critics were quick to point to photos of a less crowded parking lot, early service hiccups, or the scaling back of certain show elements like Optimus serving popcorn as signs that the project was already losing momentum. But the reality appears to be very different. Sawyer Merritt shared on X that the Tesla Diner still had over 30,000 burger orders and 83,000 fries orders in Q4. The diner generated over $1 million in revenue in Q4, a $4 million annual run rate, which is more than the average McDonald's. Okay, what we're seeing here is something pretty normal. Any space built around experience and curiosity goes through a post-hype adjustment phase. Once the initial novelty wears off, visitor numbers naturally settle into a more realistic baseline. That's especially true for a location that's simultaneously a restaurant, a supercharger station, and a brand-driven entertainment destination. Media outlets lumping routine operational adjustments together with Tesla's broader challenges to spin a failure narrative says more about click-driven sensationalism than actual performance. To be fair, Tesla Diner has moved past the loud, festival-like atmosphere of its opening days, but that phase was always temporary and never expected to last. A slowdown in foot traffic doesn't mean decline. In fact, the diner is still doing exactly what it was designed to do: boosting supercharger usage, generating steady revenue, and strengthening Tesla's brand presence in one of the most competitive EV markets in the US. It's less a struggling restaurant and more a functioning commercial testbed. Meanwhile, we're noticing a quieter but very meaningful shift happening in China. Tesla is rolling out interior upgrades across the entire Model Y lineup, regardless of trim level. Features that were previously exclusive to higher-end versions like Performance or Model YL are now making their way into standard and premium trims, a clear signal that Tesla is redefining what base model really means. Since the launch of the Model YL early last year, that version quickly became the new benchmark for the entire Model Y family. With its longer wheelbase, improved materials, and noticeably better interior experience, the YL unintentionally raised an uncomfortable question. Why don't the other versions meet the same standard? Now Tesla seems to be answering that question through action, gradually pulling the standard models closer to the peak they themselves established. As a result, the once clear hierarchy within China's Model Y lineup is starting to blur. Buyers of the rear-wheel drive version, traditionally seen as the entry-level option, now step into a cabin that feels remarkably similar to the most expensive variant. Visually, in terms of materials and overall spatial feel, the experience remains minimalist yet premium, perfectly aligned with the design philosophy Tesla has pursued since day one. The most noticeable change is right above the driver's head. The light gray headliner, long associated with lower trims and a detail that's been controversial for years, has officially been phased out. In its place is a black Alcantara-style finish that was previously reserved for performance models, and so popular that many owners were willing to retrofit it aftermarket. Standardizing the headliner color not only makes the cabin feel more upscale, but also signals Tesla's push to simplify its production line. At the same time, the center display has been upgraded to match higher-end variants. Model Y standard and premium trims now come with a 16-inch touchscreen, replacing the previous 15.4-inch unit. On paper, that increase may seem minor, but from inside the car, the difference is immediately noticeable. The larger display area, slimmer bezels, and improved contrast and resolution make the entire interface feel cleaner, more modern, and noticeably more open. More importantly, using a single display across multiple trims isn't just about aesthetics. It reflects Tesla's broader manufacturing philosophy: maximum standardization, fewer unique parts, and greater supply chain efficiency. We wouldn't be surprised if this screen design shows up in future Model 3 updates as part of a wider strategy to unify Tesla's entire product lineup. For now, these upgrades are limited to vehicles rolling out of Giga Shanghai. But if Tesla's past behavior is any indication, this is rarely the final stop. The Shanghai factory often serves as a manufacturing test lab, where changes are trialed before being rolled out to Giga Berlin and Giga Texas. As Tesla continues to prioritize efficiency across costs, supply chains, and perceived product value, phasing out older components in favor of a new interior standard makes strategic sense. Once existing parts inventories are exhausted, these upgrades are likely to become global defaults, allowing Tesla to both streamline production and stay competitive in an increasingly cutthroat EV market. Recently, Elon Musk made waves again by talking about the Tesla Roadster with a shockingly blunt statement: safety is not the primary goal. He went on to say, "If safety is your number one priority, don't buy the Roadster," a comment that immediately reignited hype around the long-awaited car. The remark wasn't just bold marketing, it revealed Musk's fundamentally different mindset toward a sports car that's been anticipated for nearly a decade. At a time when Tesla is rapidly pivoting toward robo-taxis and full autonomy, Musk wants to position the Roadster as a kind of final legacy car. He compares it to legendary supercar brands like Ferrari, where buyers prioritize excitement and performance over practical safety features. According to Musk, the Roadster will be the best of the last cars driven by humans. That line suggests that even as the world moves toward automation, Tesla intends to preserve a pure, high-performance machine for those who crave full control behind the wheel. Musk has now officially confirmed that Tesla is targeting a product demo on April 1, 2026. He joked that choosing April Fool's Day gives him plausible deniability if the event gets delayed again. Still, he insists this will be the most insane demo Tesla has ever done. The Tesla CEO describes the Roadster as a mashup of every James Bond car ever made, packed with technology that goes far beyond today's automotive norms. The biggest highlight remains the SpaceX collaboration package. Musk continues to promise a 0 to 60 miles per hour time of under 1 second. To hit that almost physics-defying number, the car would use cold gas thrusters. When asked whether the car could actually fly, Elon Musk hinted at the possibility, only adding more fuel to the excitement among fans. Even though the public debut is expected in early 2026, Musk also noted that mass production would begin roughly 12 to 18 months later. That means the first customers, many of whom put down deposits of hundreds of thousands of dollars back in 2017, may not actually get their hands on the steering wheel until 2027. Thanks for watching. If you enjoyed this deep dive into Cybercab, hit like, subscribe for more Tesla updates, and let us know your thoughts in the comments below right now today.